Justyna Zawalska. I work at Quantum Computing Laboratory at Academic Computer Center CYFRONET, and I'm a PhD student at AGH University in Poland. Together with my colleagues Katarzyna, who is also present here today, Mariusz and Tomasz, we are working on workflow scheduling using quantum devices. This project is a part of EuroHPC PL undertaking. The workflow scheduling problem is a combinatorial optimization problem defined as follows. We have a set of tasks, and the tasks are only classical, and a set of machines. For each task, there is a defined time that it takes to execute it on each machine and an associated with that cost. The goal is to find the best assignment of machines to the tasks so that the cost of using the machines is minimized, and the following conditions are met. First of all, if there is a directed path between two tasks, the children tasks can start before the parent tasks have finished. Secondly, all the tasks have to finish their execution before the deadline. The input consists of a description of tasks and machines and the deadline. Task DAC is created based on using WF Commons workflow instances that describe workflow executions. Here we use a small DAC with 22 tasks representing sample SRA search workflow. Also, we need to provide a file with a description of the available machines and their resources. Here we use HPC machines available at Academic Computer Center CYFRONET. Finally, we need to provide a numerical value for the deadline. To assign machines to tasks, we use two hybrid quantum classical algorithms. The first one is quantum annealing optimization that is performed on the D-Wave quantum computer. The second is the quantum approximate optimization algorithm that is executed on a gate-based quantum computer. The result of this hybrid quantum classical optimization is the schedule that has assigned machines to tasks. The system architecture is as follows. To create a workflow scheduling problem, we use a workflow instance in a WF format. Apart from using the workflow generator that is available from the WF Commons framework, we also created a workflow generator that can create very small workflow instances. It was necessary to create such generator because apart from workflows with many tasks, we also need to have workflows with small amount of tasks to fit the architecture of current gate-based quantum computers. When it comes to solvers, we offer a quantum annealing solution based on D-Wave CQM sampler, quantum approximate optimization algorithm written in PennyLane, which is currently being integrated, and a classical solver, Gurobi, which is just a reference method. Let's quickly see the demo. So first of all, we need to import two files. The first one is a task file. The second one is the machines file, and they have this. They are JSON's file, and they have WF format. So they simply describe the workflow and the machines and the tasks. So here's a sample workflow we are using, and in here we have a description of the machines and their details. The next thing, we need to define the deadline, so as to know what's the constraint for our workflow. Then we use this CQM solver from D-Wave. When the solver finishes, we get the result. This graph is more important from the perspective of checking out the solution and seeing if it might be correct or incorrect. But what's most interesting for us is this calculated workflow. We have machines assigned to the proper tasks, and we know how they should be executed. And this brings us to the end of this presentation. I will share the link to this demo in our Google Docs. Thank you.